Okay, so welcome to today's class. There's a couple of things I'd like to share with everyone. First and foremost, they're just a friendly reminder. We do have a big test coming up, and I want to let you know about it. It is basically exam number 1 is on Wednesday, February the 10th at 8:30 in the morning. You have until from 8:30 till 10:20 to write it, and it's worth 20% of your final grade. So the outline is right here under the assessments tab in the meta page. So the outline is called Exam 1 W for Winter 2021 outline, and that is the outline I would follow to study for this exam. So it goes through definitions, frequency tables, graphing, measures of center, measures of variation, which is the topic we're going to be discussing today, measures of relative standing, and then it goes through like the marking scheme of how much each question is going to be worth, 4 marks, 5 marks, 8 marks, 7 marks, 11 marks, 10 marks, so on and so forth. And then it gives you a couple of like hints in terms of sig figs and units. You want to make sure that you include your units in every calculation that you're doing. So that's just a friendly reminder that you do have a test coming up in about 10 days. And this is an outline, and I would use this outline as my, as just basically a skeleton as to what I'm going to pay attention to study. And just go through the notes, study your best and do the best, and do your best and forget the rest. And that's just a friendly reminder as what's coming up. Okay, any questions about that? I think that's going to be coordinated by someone else. I don't know if I'm going to be overseeing that or if that's going to be overseen by someone else, but I will get back to you on that one. So let's start off with today's notes. So today's notes, we're going to be looking at variation. So variation in the data, whenever we have data that's more variable. So this is chapter 3.2 in your textbook. So if you want to read along, or if you want to do some supplementary readings, chapter 3.2 and 3.3 would supplement today's lecture. So we're talking about measures of variation. So what is variation? Variation refers to how spread out the data values in a particular data set are. Data sets with a narrow range have low variation. So we have an example. If you have a data set with low variation, you're going to have basically a data set that looks like this, where there's very low variance. And then you could have a data set that has more of a broad range, and that would have high variation. So this would be high variation. And then the one in blue would be low variation. Low variation. I'm trying to spell variation right here. Okay. So data sets with very broad range have high variation. Variation can be expressed in 3 different ways. We say range, sample standard deviation, or population standard deviation, which is the Greek letter sigma. Variation with reference to the mean. So high variation means that the data is more spread out around the mean, which is what I was just drawing over here, actually, just in a different way. So some measurements are very far from the mean value. The mean or average is less meaningful when there is a high variation in the data points. So C has the most variation, B has the next variation, and A has less variation because more of the data points are closer to the mean being the absolute center of these normal distribution graphs, A, B, and C. Low variation means that most of the data points are very close to the mean, as they are in A. So here we have a treatment with high variation. And then next we have a placebo, and the placebo has lower variation. Okay, so that has to do with variation. Next topic is the range. So the range. The range is the difference between the minimum and the maximum values in the data set, and it's sensitive to skew and outliers. Quick to calculate, but not particularly accurate measure of variation. Range is equal to maximum value subtract the minimum value. So it's very easy to calculate. So example 1, the following data sets include the heights in inches of 5 starting players from 2 different basketball teams. So we have the Cleveland Cavaliers, and they give us 5 different heights. And next we have the Golden State Warriors with 5 different heights. Calculate the mean for each data set. So the Cleveland Cavaliers, I'm just going to represent Cleveland Cavaliers with a CC. Their mean height, which is x bar, is equal to the sum of all x's divided by the number of x's. So that's a formula you're going to have to memorize, I think, for the test, is the average formula. Okay, so we add up all of our x's, so that would be 77 plus 78 plus 79 plus 80 plus 81. So we're just going to find the average of all the heights. So 77 plus 78 plus 79 plus 80 plus 81. And then we divide by the number of x's. So there's 5. So 77. This would be a great time to have your calculator out too and calculating this with me. 78 plus 79 plus 80 plus 81 is 395 divided by 5. Divided by 5 equals 79. So that's the average height of the basketball players for the Cleveland Cavaliers. Now for the Golden State Warriors, I'm going to call this GSW. It would be 71 plus 77 plus 79 plus 84 plus 84, and divide that all by 5. What we get is 71 plus 77 plus 79 plus 84 plus 84 equals 395. We divide that by 5, we get 79. So they have the exact same averages. We should also include units in our answers. So 79 inches and 79 inches. So they both have the same average. Calculate the range for each data set. So I'm just going to go up top here and do calculate the range for the Cleveland Cavaliers, which is the maximum data value subtract the minimum data value. The maximum data value is 81. The minimum data value is 77. So 81 minus 77 is equal to 4 inches. So that's the difference between the maximum, or the tallest player, subtract the shortest player on the team. Golden State Warriors, the range is going to be the maximum, subtract the minimum. The tallest player is 84 inches, minus the shortest player is going to be 71 inches. So 84 minus 71 is equal to 13 inches. So that's the way we would calculate the range for each of the data set. What do the results of each team indicate? So they have, on average, they have the same heights, the same height of player, but the ranges of their players are vary greatly, because basically 13 inches is much greater than 4 inches, just from looking at it, with respect to 79 inches. Okay. So any questions on calculating the range or the mean of basketball players?
Could you just re-explain quickly just what the formula is for calculating mean, just what the letters all mean?
Yeah, so x bar is the average, and the average is equal to the sum of the x's divided by the number of x's. So the sum is this Greek letter sigma, the sum of all x's divided by the number of x's. So the number of x's, you just count them. So there's 1, 2, 3, 4, 5 x's. And you just add up all the x's at the numerator. So like that's 77 for the Cleveland Cavaliers, that would be 77 plus 78 plus 79 plus 80 plus 81. You divide by the number of x's, which is 5. For the Golden State Warriors, that would be 71 plus 77 plus 79 plus 84 plus 84. And that would be equal to 79 inches. So they both have the same average. We just sum up the x's and we divide by the number of x's to calculate the average. That's what this formula means right here. Does that make sense?
Yes, thank you. I was just like making sure that I like knew what all the letters meant and everything. So I'm good. Thank you.
Okay, no problem. All right, so next topic is actually, I should ask if there's any more questions before I go to the next topic. Are there any other questions? Nope. Okay, let's go to the next topic. The next topic is standard deviation. So here we have a formula. The standard deviation refers to the variation around the mean. It can never be negative. It can be 0, but if all the data, but only if all the data points are exactly the same. Standard deviation increases dramatically if there are outliers. Larger standard deviation equals higher variation. The units are the same as the original data points. So the standard deviation is equal to the square root of the number of data points that you have. So that's what n is. The sum of x's squared, subtract the sum of x's, and then close bracket squared, and then divide by the number of data points that you have, bracket number of data points that you have minus 1. Okay, so that's what this formula is. And it's just important to break it down into steps and just say, okay, do I know what n is? Okay, then plug it in. Do I know what the sum of x squared is? Then I plug it in. Do I know what the sum of x is? Plug it in. Do I know what n is? Do I know what n minus 1 is? So you just break it down into 1, 2, 3, 4, 5 chunks. Okay, so let's calculate the mean. Using the following pulse rates of males, all in beats per minute, calculate the following. Okay, so what I'd like you to do is calculate the mean, and I'm actually going to break it up into breakout rooms for about 1 minute, and I'd like you to calculate the mean of 84, 74, 50, 60, and 52. Okay, so write those numbers down: 84, 74, 50, 60, and 52. And remember, the formula for mean is x bar equals the sum of all x's divided by the number of x's. Actually, I'm not going to do breakout rooms. It'd probably take too long for that. Actually, yeah. So once you have the mean, I'd like you to type it into the chat, and just so that we can actually have some participation in this class. All right, so once you have the mean, just type it into the chat and we'll see what you get. I'm going to calculate it too. Okay, so already somebody's typed it into the chat. Let's see what. So we have from Yusuf, Emma, and Victoria, 64. All right, so it looks like 64 is the average. I'm just going to type this into my calculator. So 84 plus 74 plus 50 plus 60 plus 52 is, so it's basically 320 divided by 5. So I've added up 84, 74, 50, 60, and 52 equals 320 divided by 5. 320 divided by 5 is equal to 64. And don't forget your units. Units always go with the mean, beats per minute. And they also go with the standard deviation as well. All right. So for the standard deviation, we're going to set up a different table. So we have our x's, and then we're going to have our x's squared. So x is 84, but now we're going to have to square 84. So that's 7,056. Then we're going to have 74, but we're going to square 74. So 74 squared is equal to 5,476. Then we're going to have 50 squared equals 2,500. Then we're going to have 60 squared. The reason why I'm squaring this is look at what is happening here in this formula, right? We have x squared, so that's why we need to square our x's. So 60 squared is equal to 3,600. 52 squared is equal to 2,704. Okay, so now we have our x's squared, and now we need to sum up all of our x's squared. So I'm going to add 7,056. So I'm going to start right here. 7,056 plus 5,476 plus 2,500 plus 3,600 plus 2,704. And the sum of all x's squared equals 21,336. All right, so now I know what this, my n is equal to 1, 2, 3, 4, 5. I have 5 pulse rates. So n is equal to 5. So I know what n is. I know what the sum of x squared is. The sum of my x's is just going to be 84 plus, oh, the sum of x's, I've already done that. The sum of x's is 320. Now, the sum of x, actually, let me just write that out a little differently here. The sum of x's was equal to 320. I already did that calculation for my mean. So now I'm going to find the standard deviation with all the information I have. I just don't want to lose that formula. I really need that in order to do the calculation. So the standard deviation is equal to the square root of n. N is equal to 5. So I'm going to substitute n is equal to 5 into my formula. Bracket the sum of x squared. So the sum of x squared is bracket 21,336. Close the bracket off. Bracket 320, and then that's going to be squared. And then I'm going to divide by n, which is 5, multiply by n, subtract 1. So 5 subtract 1 is equal to 4. So any questions about how I got to this point? I'm just going to start off. No? Okay, I don't hear any questions. All right, so then that means I'm going to go ahead. So 5 times 21,336 equals 106,680 minus 320 squared, which equals 102,400 minus 5 times 4, which is 20. Square root that. So now we have 106,680 minus 102,400 equals 4,280 over 20. So we divide that by 20 and we get the square root of 214. All right, just in the nick of time, I was running out of space. So 214, the square root of 214 is equal to 14.6, and I'll keep a couple extra decimal places since that's what statisticians like to do. They like to keep a couple extra decimal places. So 14.63 beats per minute.
I got the same.
Okay, excellent. Thank you. Thank you for that confirmation, Ben. Sorry. All right.
Thank you.
So now this is what our standard deviation is. And we have our mean. Now, this is a concept that's going to be coming up in this class, is whether or not a value is statistically significant or not. And I'm going to tell you if it's more than 2 or less than 2 standard deviations of the mean, then it's going to be considered statistically high, or it's going to be considered statistically low. But we'll get to that in a moment. So I'll come back and I'll revisit this in about 20 minutes from now. Okay, so we solved for the mean. of the pulse rate, and we solve for the standard deviation of the pulse rate using this formula. Now, there's something I'd like to show you with regards to the exam that's coming up, and it's called the formula sheet. And I just want to make sure that you know what is going to be on the formula sheet. Let me just share that screen with you. Share the screen. So it's this formula sheet. And so the formula we just used, I just want to show you, it's right here. Yeah, so the formula we just used is actually going to be on, the formula that we just used is going to be on the formula sheet. So this formula sheet, you're going to be using a lot of the formulas at the top left of the formula sheet, just so that you get used to looking at this formula sheet, so that when it comes time to your exam, you know what you're looking at and you know where to find it. So that, anyway, we just use this formula right here. Okay, so that's for ungrouped data, or data that comes as individual data points, as in it's not coming in a table. All right, any questions for how we got this standard deviation? It took a lot of math, a lot of number crunching, and a lot of hanging in there, but that's how we got the standard deviation there. Any questions? We got 14.63 beats per minute as the standard deviation. Now, something you might want to ask yourself is, does this answer make sense? And on the order of magnitude of the question, the mean is 64. The standard deviation shouldn't be higher than the mean. Okay, so it's a fraction of the mean. So therefore, yeah, we're on the right order of magnitude. As in, if I got like 100, then it would probably be too much. So I would have made some sort of computational mistake. All right, so let's use, let's go back to that table. So right here, we're going to find the mean using this formula. So the mean is equal to the sum of all x's divided by the number of x's. So I'm going to use that formula to solve for the next question. So the next question is asking, let's find the mean for the football players on this team. So x bar is equal to the sum of all x's divided by the number of x's. So this is equal to, if we add up every single one of these weights, so that's what I'm going to do with my calculator. Now would be a good time for you to practice as well. So 189 plus 254 plus 235 plus 225 plus 190 plus 305 plus 195 plus 202 plus 190 plus 1252 plus 305. So we have the entire 11 football players weigh 2,542 pounds. And then we divide by the number of football players. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we're going to divide by 11. And this will equal, on average, the football players weigh 231.09 pounds. Okay. And so that's how we get the mean weight. And then to get the standard deviation, we're going to use the same formula. So we're going to square all of our x's. So at this point in the game, at this stage, what we could do is actually, I'll show you how to use Excel. So what we could do, oh, somebody has their microphone on. If you could mute your microphone, please. Yeah, so at this point, what we could do is actually use Excel to calculate the standard deviation. So or we could use the formula. So let me think about that. Now, yeah, so what I was thinking is what we could do is just use Excel and have Excel calculate the standard deviation. So can you see my Excel spreadsheet? So what
Yeah.
what I could do is I could type in 189, 254, 235, 225, 190, right? 305. And this is way faster, right? And you'll have Excel on your exam or on your test. So why not use Excel if you can make it easier on yourself? So this is another way to calculate the standard deviation, is just put in all the numbers into Excel, right? Why not? 252, you just got to make sure that you're adding them or you're entering them accurately. So I've entered all 11 football player weights. So now what I'm going to do, can you see my Excel spreadsheet now?
Yeah, we can see it.
Okay, so the formula for standard deviation is STDEV. And what I'm going to do is open bracket that and then close bracket enter. So my standard deviation is 43.85. So I can write that down. The standard deviation equals 43.85. Now, what I could do as well is calculate this the long way using the formula. So using the formula, what I could do, right, I need a couple of pieces of information to get to calculate the standard deviation using the formula. So what I need is n. N is equal to the number of data points that I have, which is 11. There's 11 football players on the team. And then I'm going to sum up all the x's squared. So 189 squared plus 254 squared. So I'm just going to do it the long way as well to see if the long way matches Excel, right? So that's what I'm doing right now is I'm going to be doing it the long way just to see if it matches with Excel. So I'm just going to write down that formula real quick. Standard deviation equals the square root of n times the sum of x squared bracket sum of x's squared over n and subtract 1. So 254 squared plus 235 squared plus 225 squared plus 190 squared plus 305 squared plus 195 squared plus 202 squared plus 190 squared plus 252 squared plus 305 squared equals. Okay, so let's bring it all back. The standard deviation formula is going to be equal to 11, which is my n equals 11. My sum of x's squared is equal to 606,670. Okay. Minus my x, the sum of all x's is 2,542. I did that calculation over here to get my my average calculation, and then I'm going to have to square that over and then 11 times 10. So let's see if the longhand calculation actually matches Excel. Of course it should, but we're just going to, and then make sure you have your units. We're just going to do this for the sake of comparison and also just for the sake of showing you that there's multiple different ways to get the standard deviation. You can use the formula or you can use Excel. Excel, of course, is much easier, right? Okay, so 11 times this giant number equals 6,673,370. Subtract 2,000 542 squared equals 6,400,061,764 divided by 11 times 10. Okay, so we have a really giant formula right here, but we're about to simplify it. So 6,673,370 subtract 461,764 equals, I'm starting to run out of space, 211,606 divided by 11 times 10, which is 110. So 211,606 divided by 110 equals, so this is equal to the square root of 1,923.69. So square root of the answer equals 43.86. What did Excel get us? 43.85. This one got us 43.859. Actually, let's have a look at Excel again. 43.85. Oh yeah, 86. So Excel got us 43.86 and our longhand calculation got us 43.86. So that just goes to show you that, you can get it via Excel if you like, or you can do it via longhand calculation, just whichever one makes sense for you. It really depends on which one you develop a comfort level with, especially if you're doing practice and homework with the longhand calculation as opposed to like the Excel calculation, whichever one makes sense for you. So type into the chat which one you think is better, longhand calculation or Excel. And then press enter, just because I'd like to do a quick survey as to what people think, longhand calculation or Excel. So go ahead. Yeah, Excel is much easier, right? You just enter the numbers directly into the cell and then you do STDEV open bracket, and then you highlight all the numbers that you want and then you close the bracket. Yeah, so Excel is much easier. You just need to know how to work the tool. So yeah, it's much easier. So I'm happy I showed you how to work Excel. So I'm going to try to incorporate that today in today's lecture, because Excel definitely takes a lot of like that longhand calculation out of it, because you could work with numbers on the order of trillions. There's billions, there's trillions, and there's millions. So anyway, I'll try to incorporate more Excel into today's lecture. All right. So back to our notes. Okay. So population parameters for standard deviation. The formula for population standard deviation provides a different answer than the formula for samples. Population standard deviation is calculated as follows. Okay, so we have sigma equals the square root of, so it looks very similar to what we were just using, equals x, or the value, subtract the average or the mean, squared, divided by the number of data points, subtract 1. This formula is not on the formula sheet and you will not need to calculate it. You will be given population standard deviations directly in the questions. Okay, so here we're now shifting gears to something that I think is very important, because it's definitely going to be on your test. So I'd like to highlight it. And it's called statistically significant values. All right. So any values between the mean plus or minus 2 standard deviations will be in the center of a normal distribution curve and would be considered common or expected measurements for the data set. Is the value unusual? Any values equal to or less than the mean minus 2 standard deviations are considered unusually low. So here we're talking about anything that resides on this end of the curve or on this end of the curve. So if we're on this end of the curve, we're unusually low. We're talking about what's usual and what's unusual. Unusually low. Whoops, that doesn't look too legible. Here, give me a second here. Okay, so this is unusually low, unusually low on this side of the data curve, and on this side is unusually high. So if we're greater than 2 standard deviations of the middle, so this is our mean, this is X bar. X bar is always in the center of a normal distribution. So if we're 2 standard deviations, right? Or this is negative 2 sigma, this is 2 sigma. So this is 1 sigma from the standard, from the mean. This is negative 1 sigma right here, negative 1 sigma. So any values equal to or less than the mean minus 2 standard deviations are considered unusually low. Any values equal to or greater than the mean plus 2 standard deviations are considered unusually high. To determine whether or not a value is unusual or significant. So this is what we are going to determine whether or not a value is unusual or whether it's significant. We're going to say X bar plus or minus 2 standard deviations. Okay, so if I go back and I say a player on this football team weighed 300 pounds, is this statistically significant, right? So what we would do is we would say X bar plus 2 standard deviations. So I'm wondering if 300 pounds is considered statistically significant with regards to the rest of the football team. So what I would do is I would take the average, which is 231, and I would add 2 times 43.86, and I would get 318.72. So if a player is within 318 pounds, then it's not statistically significant to say that he weighs 300 pounds. So, but if he was 320 pounds, that would be statistically high for his weight, right? So that's what we're now discussing, is what is considered statistically significant and not statistically significant, or statistically insignificant. Okay, so here's a couple examples. Example 1. So I'd like you to work on this and enter it into the chat when you have the answer. So I'm going to take a break for a little bit. And then I'd like you to enter it into the chat when you have the answer. But example 1, for a given data set of over 150 resting heart rates, the mean is 69.6 beats per minute. The standard deviation is 11.3 beats per minute. What values would be considered unusually low? Does anyone have an answer for that? Can someone pipe up and tell me what they would how they would approach this problem?
Well, didn't you use like the 11.3, and anything below that would be unusually low?
Okay, so sorry, who's speaking? I can't see the names. Here, let me stop my share for a sec. Okay, go ahead.
Well, so the 69 point whatever that number was, that was the average you said?
Yeah, so here I'll share it again. So the 69.6 is the average.
And
Yeah.
then are we supposed to be focusing on like what does like the 11.3 have to do with it? Like would that be what would, like anything under that would be unusually low, or would you be looking at the 69.6 to see what is unusually low?
Okay. So yeah, so 69.6 is your starting point. And then you would subtract 2 times the standard deviation, and anything lower than 2 times the standard deviation of the mean is considered unusually low. So what would be considered unusually low? Okay, Nicholas Wawia, would you like to explain how you got your answer for us? Nicholas, are you there?
Yeah, sorry, I'm here.
Okay, can you explain how you got your answer? It's correct, by the way.
Yeah, so you just take the larger number minus 2 standard deviations, and then anything below that would be too low.
Yeah, so 69.6 subtract 2 standard deviations. So what is 69.6 minus, so what is 2 times 11.3? So do you have your calculator in front of you? Are you able to tell me what 69.6 minus 2 standard deviations is?
Yeah, it's 47.
Okay, so anything, can you explain that again to the class?
So it will be anything below 47 would be too low.
Exactly. Awesome. Okay. And can you take us or explain us how you would get part B? So what values would be considered unusually high? Or
So you do the same thing, just add to it though, instead of subtract.
exactly, yeah. So 69.6 plus 2 standard deviations. So that means 2 times 11.3 is 92.2. So anything greater than 92.2 would be unusually high. That's right. So let's write this out just for those who are following along, trying to follow along with us. So let's say that what values would be considered unusually low. So it's X bar minus 2 standard deviations. So X bar is equal to 69.6 beats per minute minus 2 times 11.3 beats per minute. And this is equal to, 69.6 minus 2 times 11.3 equals 47 beats per minute. Okay. So what values would be considered unusually high? What we're going to have is X bar plus, so it's any values that are greater than this, any values that are less than. So values that are greater than 2x x bar plus 2s. So x bar is equal to, or the average is equal to 69.6 beats per minute. And then we're going to add 2 times 11.3 beats per minute. And this will equal, okay, so 69.6 plus 2 times 11.3 equals 92.2 beats per minute. All right, so example 1C, is a resting heart rate of 95.2 beats per minute unusual? Yes or no? Type that into the chat, what you think the answer is. Yeah, so I'm getting a lot of yeses. So for those of you who typed in yes, can you explain why you think this is unusually high? It's greater than the threshold, isn't it? The threshold is 92.2 beats per minute because it's over the standard deviation of, 2 times the standard deviation plus 69.6. That's correct. So thank you, Emma. All right, so example 1D, is a resting heart rate of 47.0 beats per minute unusual? All right, so let's pull out the calculator again. So 69.6 minus 2 times 11.3 equals 47. So now we have, is a resting heart rate of 47 unusual? Type that into the chat if you think it's unusual. So it's 47 beats per minute equals X minus 2S. So it's right on the borderline. So I would say it is unusual. So it's an unusual beat per minute because it's right on the borderline. So there it is. It's somewhat unusual. All right. So variance is the next topic. Any questions about how to determine whether or not a value is statistically significant or insignificant? Now, if any value was 47 to 92, it would be considered insignificant. But if any value was less than 47, it would be considered statistically low. If any value was greater than 92, it would be considered statistically high. That's just another way of thinking about that too. All right. Let's go on to variance. Variance. Variance is a measure of variation obtained by squaring the standard deviation. The notation is very simple. Sample variance is equal to S squared. Population variance is equal to sigma squared. The units for variance are the original units squared. Because the units are different from the original data, it is much easier to interpret and work with standard deviation rather than variance. Okay, so that's just a little note on variance. All that you have to do with the standard deviation is actually square it and you'll get variance. So squaring is to the power of 2, and that's how you can get your variance. All right. And with that, we're going to move on to the next topic. The next topic is finding a standard deviation for a frequency distribution table. And I'll show you how to do this using Excel, because using a calculator, it actually, as you can imagine, you start to get really, really big numbers. So I'll show you how to calculate this using Excel. So I've actually already entered a lot of the information into Excel, and I already have all of the data here, but I'm going to show you step by step how to do it. So let's just pretend we're just opening Excel for the first time, and we need to calculate how what the standard deviation is for this table. Now what you want to do is you need to know the sum of the frequencies times X squared. You need to know what N is. So N is the total number of frequencies. So you have to add up all the frequencies to get what N is. So the frequencies multiplied by X. So X is the midpoint. Okay, so I'm going to just work through this step by step, and I'll show you how to do it. It's fairly straightforward. Okay, so we're going to have our lower class here. We're going to have our upper class right beside it. Okay. Then we're going to have our midpoint will be calculated right after that. Then we can have our frequency calculated. Okay, so our lower class is going to be all these values on the left-hand side, okay? So our lower class is equal to 50 plus 70. We have 70, then we have 90, then we have 110, then we have 130, okay? Then we have 69, we have 89, we have 109, we have 129, then we have 149, okay? The midpoint is equal to the lower class plus the upper class. And then I'm going to put that actually the lower class plus the upper class. I'm going to put that in brackets. And then I'd like all of that divided by 2. So it's the midpoint between the lower class and the upper class. It's basically the average between the lower class and the upper class. And then you see how I took my black cross, my black plus sign, and I just dragged the box down because I want that formula repeated all the way down for each row. Rows go left to right, right? So I'd like that repeated for each row. Now my frequencies can be entered. So I have a frequency of 2 here, 33, 35, 7, and 1. Okay. Next, I'm going to have my frequency multiplied by my X. And then I'm going to have that to the power of 2. Okay, so how do I do that? I'm just going to actually insert one table, and I'm going to have my x's to the power of 2. Or I'm going to do my x to the power of 2 first. That's what I've just decided. So x to the power of 2, just hang in there with me. This is a process. It's going to take some time. But my midpoint is actually the x in this formula. Okay, so that's something that you need to know. Okay, can you hold on the chat, please? If you're showing Excel, we can't see it. Okay, so let me just, I should probably be sharing that screen. So let me share the screen can you see the Excel right now? Can anyone see the Excel?
Yes.
Okay, okay. So for data in a frequency distribution table, calculating the standard deviation requires adding columns to the table. The formula for standard deviation is as follows, right? So I should probably start from the beginning because I'll start from the beginning because I needed you to watch what I was doing in Excel. Can you see? You can see what's going on in Excel now?
Now we can, yeah.
Okay. Okay. So basically what I'm doing is I'm going to find the standard deviation of this table using this formula. And since this formula has really big numbers in it, I'm going to use Excel to actually tabulate the standard deviation. Okay. So I have my lower class from my table. I have my upper class from my table, and I also have my frequency from my table. Okay. Okay. And my midpoint is going to be calculated as open bracket, the lower class plus the upper class, close bracket, divide by 2. Okay, and then I'm going to take this black plus sign and I'm going to drag it all the way down because I want that formula repeated across all the rows, so all 5 rows. Okay, so I'm going to turn this into a professionally produced table in a moment, actually, whenever the time is right. Okay, so for x squared, what I'm going to do is my midpoint is considered x in this formula. Okay, so I'm going to square my x's. So I'm going to take this cell and multiply it by itself. Therefore, it's going to be squared. So x's are squared right here. And then I'm going to take in this cell, I want my f times x squared. So that's my frequency multiplied by my x squared. So that's d2 multiplied by e2 squared, or e2, which is x squared. And I want that for all of my values. Okay, so see how these get quite large. So I was doing all these calculations by hand over the weekend, and I was dealing with really, really large numbers, as you could imagine, right? Okay, so there's another table there's another multiplication that I'd like to do as well, and that's this one. The f times x has to be done as well. So f times x is equal to that'll be equal to this column. So the frequency multiplied by x, f times x, I'll just call it that, f dot x. And that'll be equal to the frequency multiplied by my midpoint, which is what x is equal to. So star asterisk is equal to, see how the asterisk there, that's equal to multiplication. All right, so 2 times 59.5. Sorry, my internet connection's a little unstable at the moment, but I'm still going to continue on as best I can. Okay, hang in there with me. I'm going to format this as a table. My table has headers. Okay, so now we have a table going on here. And now I'm going to sum up my frequency. So my frequency, oh, no. I'm going to sum up all of these values. So no, I'm going to sum up all the values. Okay, so I need to know what the sum of this is because that's what the formula needs. The formula needs the sum of f dot x squared. So that's what I'm going to do here is the sum of all of these values right here. Whoops, undo. I'm just going to actually not format my table for now, actually, because that's not adding any value to it at the moment. Okay, so sum up all of these f dot x squared. So this value is going to be very important. And then I'm going to sum up these values as well, the f dot x values. I'm going to sum those up as well. Okay. And what else do I need to do? I need to sum up my frequencies. So I'm going to sum these up. And then I'm going to add in a border just to show that I'm doing some summations here. Okay, so these are my sums. Now I have all the information I need to actually do, to complete this formula to calculate the standard deviation of this table. Now, we were calculating the mean of this table earlier in one of the earlier notes. And so we will actually be calculating the mean and the standard deviation of tabled data. But now we're just going to focus on how to calculate the standard deviation. So now I have all the information I need to go ahead and calculate the standard deviation. So give me 1 second here. Do you see, yeah, you probably see my screen here. Okay, so what I'm going to do is actually write this down. Okay. I need to actually write this down right here. Okay. So I'm going to actually start to draw out this formula over in my other document. So can you see me writing down the 78? Can you see me writing that down?
Yes.
Okay, so now I'm going to start filling in all the information I just calculated using Excel. So 78 times 681,579.5 subtract 7,201 squared over 78 times 77. So that's what I've calculated using Excel instead of doing it by hand. So I could even do the rest by Excel if you wanted, or you can do the rest by calculator. I'm going to just finish it off by calculator because it's pretty hard to explain like over the internet how to do this, as you can imagine. But we're going to just try to finish it off by hand now. So 53,163,201 minus 7,201 squared is equal to 51,853 or 54. Let me write this down. 54,401 divided by 78.77. Okay. So 53,163,201 minus 51,854,401 equals 1,308,800, just 800 divided by 78 times 77. So this equals the square root of 217.9 All right, so the square root of 217 square root of answer equals, so this, the standard deviation of this table equals 14.76. Now, if I was to continue my calculations using Excel, this is what I would do, is I would take this value, the 7,201. So I would take this value and I would multiply it by itself. So multiply this by G7 again. I take G7 and I'd multiply it by itself to get this value, the f dot x squared value, okay? And then I would take this value right here, the 681,579, this value right here. I would take that and I would multiply it by 78. So I would have this value multiplied by 78. And then I would basically be subtracting equals this value, but the 5 million value, I think, yeah, 5 million, subtract the 53 million value, subtract the 51 million value. That's what I would do. Then I would have this value divided by 78 times 77. And then I would find the square root of this value. So I would go SQRT, which is square root. That's a square root function, close bracket, and then that would give me 14.76, which is the answer for the standard deviation for this table. So you could use Excel or you could use a calculator. Both ways get you the same information. And both ways we're using this formula on the formula sheet. Or actually it's this formula right here. So this is using a frequency table, how to get a standard deviation from the frequency table. So likewise, we could actually calculate the mean from the frequency table. So if I was to ask you, please calculate the mean from the frequency table, that's what this would look like, is f dot x over the sum of the frequencies. Now, are there any questions with regards to how we obtained the standard deviation from the frequency table? We got 14.76 as our standard deviation. Any questions regarding how we got to that point? We did step-by-step using Excel. We also did a bit of hand calculation, and then we followed up with Excel as well, and we got 14.76 both ways. Okay, so now I'm going to ask what values are statistically high and what values are statistically low. And what we need in order to determine that is that we need to know what the mean is plus 2 standard deviations, and then we need to know what the mean is minus 2 standard deviations in order to determine what IQ scores are unusually high and what IQ scores are unusually low. So this is the formula for mean of a frequency distribution table. I just got it from this this formula sheet right here. Are you following, by the way? Is the screen sharing the correct? I hope it's sharing the correct one. So yeah, this is how we calculate the mean from a frequency distribution table, right? We need to know the frequencies and we need to know the midpoints. That's what X is. X is a midpoint and F is the frequency. And then this is the sum of all the frequencies. Okay, so back to our question. Our question is, so we're going to find basically what the mean is of the frequency distribution table. So I'm going to pull back Excel because Excel actually calculated all of our midpoints for us. We had okay, so our midpoints were 59.5. Oh, I need Excel. I just need Excel. Hold on a sec. I'm just going to try to resize this so I can have Excel here. 59.5, 79.5. We had 99.5 as our midpoint. We also had 119.5. We have 139.5. Okay, so we know what our midpoints are. We know what our frequencies are. Therefore, we can calculate the mean of this frequency distribution table. Okay, so X bar is equal to the frequency, so 2 times the midpoint, which is 59.5. And then we're going to add this up, not multiply, add. So add 33 times 79.5. Just give me a minute. I'm just trying to make this a little bit clearer. Okay, plus 35. Oh, 35, not 33. 35 times 99.5 plus 7 times 119.5 plus 1 times 139.5. And then we divide by the total, the total sum of all frequencies. So that's 2 plus 33 plus 35 plus 7 plus 1. So what is the sum of all of our frequencies? I'm going to wait for someone to type that into the chat. Do we have a sum of all frequencies? The sum of F? Or what's going to go on the denominator here? Yeah, so Emma is saying 78. That's correct. So 78 goes on the bottom. So the average of the frequency distribution table is going to be equal to the frequency. So 2 times 59.5 plus 33 times 79.5 plus 35 times 99.5 plus 7 times 119.5, 119.5 plus 139.5. So this is equal to 7,200.4 over 78. Divided by 78 equals, so on average, we have an IQ score of 92.31. So what IQ scores would be considered unusually high or unusually low? I'm going to set you out into breakout rooms for you to discuss that for the next 5 minutes, and we'll check back in at 10:45, okay? So I'd like you to discuss what IQ scores are unusually high and unusually low. Just write these two numbers down. You need to know what the mean is. The mean is 92.31, and the standard deviation is 14.76. So those are the only two numbers you need to know right now is X bar, and the standard deviation is 14.76. So if you can write those two numbers down or try to remember 92 and 14. So 92 is the mean, 14 is the standard deviation. I'm going to set you out into breakout rooms, and I'd like you to discuss what numbers are considered unusually high and what numbers are considered unusually low. Any questions? All right, we're going to go into breakout rooms and come back at 10:45.
Miss.
Okay, so how did those breakout rooms go? What did you discover, or what did you find out for what IQ scores are unusually high and what IQ scores are unusually low? Would someone like to jump in and say what IQ scores are unusually low? Class, are you there? Hello?
I couldn't see the table, but I got like the unusually low, like
Okay, what did you get?
for unusually low, I got 62.79.
Okay, let me just double check and see if that's correct. So how did you calculate it?
I did the mean minus 2 standard deviations.
Okay, so the mean minus 2 standard deviations, and then you got, so anything less than, what did you get? 62.79.
79.
Yep, I got the same thing. All right. And then what about IQ scores that are unusually high?
Anything greater than 121.83.
Sounds right. Awesome. So again, it was calculated. It's basically the mean minus 2 standard deviations, and then it's the mean plus 2 standard deviations. Excellent. Yeah, so 92.31 plus, and then 2 standard deviations. So 2 times 14.76 equals 121.83. Excellent. So anything greater than 121.83 is considered unusually high. All right. So here we have another table. In this table now, it's a pulse rate, and it's saying calculate the mean and the standard deviation for the following data. So I'm going to walk you through how to do it one more time. So please pay close attention on how to do this. So I'm going to pull up my Excel spreadsheet, and my Excel spreadsheet is going to help me out here. So I'm going to enter my lower class. And I'm also going to enter my upper class. Then I'm going to calculate my midpoint. Then I'm going to enter in my frequency distribution table. So this is how we're going to calculate the mean and the standard deviation for the following data, right? So we're going to need to know what the lower class is, which is 40, 55, 70, 85, 100, okay? The upper class is 54, 69, 84, 99, 114. Okay. Now my midpoint is calculated by doing close bracket, lower class plus the upper class, divide by 2. All right. Now, all right. So now I've calculated my midpoint, and what I did was I just found that black plus sign, and I dragged it all the way down.
Miss, we can't see your Excel.
Oh, okay. Sorry about that. Okay, so let's start that over again. It should be sharing my screen. Do you see both Excel and the PowerPoint that has or the Word document that has the pulse rate and frequency? You should see the Excel now and the pulse rate with the frequency. Do you see that?
We can see both.
You can see both? Okay, good. Okay, so the way I calculated my midpoint is, I'm going to add my lower class to my upper class, and then I'm going to divide by 2. Okay, so that's obviously not doing it correctly. So I need to add in brackets. So it's going to be bracket lower class plus my upper class, and then I have to close the bracket and then divide by 2. So it's very important that you add in brackets there. Otherwise, it's not going to calculate the correct midpoint. Then I'm going to have my little black plus sign, and I'm going to drag that formula down because I want it to repeat for every single row. Now I have my midpoint calculated. My midpoint, by the way, is the X in the formula. My formula, of course, is this one. And by the way, that formula is this one. This is the formula that you're going to be using on your test that's coming up February 10th, on Wednesday, February 10th at 8:30 in the morning. This is the formula you're going to be using for the standard deviation calculation. Okay, so back over to that Excel. Okay, so I have my midpoints now calculated. So now I need to know what my frequencies are. So the frequency is 15, 63, 62, 11, and 2. All right. Now I need to sum up my frequencies. Well, actually, I do need that. I do need the formula. So I'm going to actually keep this formula right here, just so I know what I need to do in terms of all of my columns. So I'm going to have to multiply my frequency times x. So I'll just put f times x. So the frequency times my midpoint is equal to frequency. So this D15 and then asterisk multiplied by 14, D or C15 equals 705. So now I have all of my multiplications taken care of, my f times x. X squared is going to be the next thing I do. So x to the power of 2. So x squared or x multiplied by itself is just going to be equal to this value multiplied by itself. And then I'm going to drag it down and make sure that it basically repeats again and again. So C15 times C15, C16 times C16, C17, C18, C19 times C19. So it's going to be squared. So it's just a number multiplied by itself. And then for that formula, I need this value right here. So f times x squared. So that'll be the next thing that I do is basically f times x squared. Okay, so my frequency times x squared, so that's going to be equal to this column multiplied by x squared, which is going to be equal to this column. And then I'm going to repeat that for every single row. And then in order to sum these all up properly, because I need to sum, that's what this value, this sigma value in the formula, the sigma, the Greek letter sigma means sum it all up. So I'm going to have to sum everything here. So I'm going to format that a little bit and say sum. So I'm going to sum up my frequencies. This will be equal to, these will be equal to the sum of all my, my frequencies. So I'm going to sum up everything above that cell, which is 153. And then I'm going to sum up everything above this cell, which is going to be equal to, 10,600. And then I'll sum up everything in this cell. So I'm going to sum all, whoops, I think I made a little bit of a mistake there. Okay, sum up everything in above this cell. Okay, so now I'm getting one step closer to finding the standard deviation for this formula. Yeah, so now what I need is, I just need that formula. So I'm going to actually go over to, okay, let me just follow something over here. Okay. I just need this formula actually. So I'm going to write it down. Why don't I just, I'm going to calculate it using Excel. So what I need to do right now is actually take this value and square it. So I'm going to take this value right here and square it. So it's going to be equal to this value multiplied by itself. Okay, so I squared this value. And then I'm going to take this value right here, and I'm going to multiply these two values together. So I'm actually just working the formula at the moment. So it's basically n, which is 153. So see how there's an n here, times f dot x. So f dot x squared. Oh, I think I just did the wrong thing here. Hold on a sec. Delete. Okay, let me just backtrack a second here. So f dot x squared, this is the value that I have to square, is the value right above the cell that I'm in right here. So this value times itself. Okay, and then I'm going to take Okay, so hold on 1 second. I just need to write this formula down. Okay. So there we go. Okay, so now I can write the formula down, and I can use the values that I just calculated. There we go. So okay, so this, I just have to make sure that I'm using the right values. Okay, so back over to Excel, f.x squared is this value. So I'm going to take this value, which is the one that I squared, and I'm going to take this value and multiply it by n, which is 153. Okay, so now I'm going to subtract these two values. So this value right here, subtract this value right here, equals that value. And then I'm going to divide it by equals this value divided by 153 times 152 equals 151. And then I'm just going to find the square root of the above value, 151. So there's 12.3 is what I'm getting as the standard deviation for this table. So the table here is standard deviation is equal to, standard deviation is equal to 12.3. So let me explain how I got to 12.3. If I was to substitute in all of these values, basically, so what I would, basically here, I'll show you how I actually found all of these values. I have to actually show you how I did that, right? So, so n is equal to 153. And what n is equal to is the sum of all frequencies. So I have to add up all my frequencies together. So it's basically 15 plus 63 plus 62 plus 11 plus 2 is equal to 153. So that's what n is equal to. My frequency times my x squared, or the sum of the frequencies times x squared is equal to 7,500 7,058 or 758,907 subtract. So there's a multiplication sign right here. And then we're square rooting this whole thing. So it's this value. I found a value right here in Excel, right? And then f.x squared is this value right here. So it's basically equal to 10,611 squared, okay? Those two subtracted, 153 times 152 is on the denominator. Anyway, all this equals, it comes down to 12.3. So that's the way you can use Excel. So what I did with Excel is basically I just did all of these big multiplications using these cells, right? So I did this giant subtraction was using Excel, and then the giant division of whatever was on the numerator, I just took that and I divided it by 153 times 152. And what that got me was the square root of that number is 12.3. So what we need to know, actually, we need to figure out as well what the mean is of this table. And to calculate the mean, we also need to figure out the mean. Okay, so the mean of this table is going to be found using x bar is equal to the sum of the frequencies times x divided by the sum of the frequencies. So x bar is equal to the sum of the frequencies dot x divided by the sum of the frequencies. So fortunately, again, using Excel, we know what our midpoints are. So knowing what we know about our midpoints. So our midpoints are 47, 62, 77, 92, and 107. So knowing how to calculate our mean, we're going to calculate 47 times 15 plus 62 times 63 plus 77 times 62 plus 92 times 11 plus 107 times 2. And then we divide by the sum of all the frequencies, which is equal to 153. So fortunately, this one's a lot easier. Finding the mean is much, much easier. So 47 times 15 plus 62 times 63 plus 77 times 62 plus 92 times 11 plus 107 times 2 equals 10,016 plus, or sorry, 10,611 plus, or divided by 153 equals 69.35. So we know what our mean is, and now we know what our standard deviation is. So now we can determine what pulse rates are unusually low, and we can determine what pulse rates are unusually high. So how do we determine what pulse rates are unusually low? Again, we use the x bar minus 2 standard deviations. So that's basically 69.35 minus 12.3 times 2. This is all in brackets. And don't forget the multiplied by 2. I almost forgot to multiply by 2. So 69.35 minus 2 times 12.3 equals 44.75. So anything lower than 44.75 would be considered unusually low. Any pulse rates that are considered unusually high would be 69.35 plus 2 times 12.3. All right. And that would be equal to 69.35 and then plus bracket 2 times 12.3, close bracket. Anything greater than 93. Oh, I should actually put in my units, of course, beats per minute. 93.95 beats per minute. All right. So that is how you would use, how you would calculate the mean of a frequency distribution table and how you would calculate the standard deviation of a frequency distribution table, and then determine whether or not any values are statistically high or statistically low. Any questions about those topics? because we have time to dive into the next series of topics. All right, with that, let's dive into the next series of topics. So let's see what we can make it through in the next 15 minutes. So measures of relative standing, Z-scores. A Z-score is a value that represents the number of standard deviations from the mean. So like we've been using, 2 is the measure of standard deviation that determines whether or not something is statistically significant. A Z-score is a value that represents the number of standard deviations from the mean for each data point. Each data value will have a different Z-score that tells you how many standard deviations plus or minus the value is from the mean. Z equals X, so that's a data point, minus X bar, which is the average, subtract the S, which is the standard deviation. Or Z equals X minus mu, which is the population mean, minus sigma, which is the population standard deviation. Rules. Z-scores are always rounded to 2 decimal places because of the Z-score table, there's no units. And rule number 3, negative Z-scores indicate that data point is lower than the mean. Positive Z-scores indicate that the data point is higher than the mean. Recall that data equal to or beyond 2 standard deviations is statistically significant, unusually high, or unusually low. Therefore, data points with a Z-score of plus or minus 2 or more are statistically significant values. So here we have Z-score values that are less than 0. So they're significantly low values if they're less than 2. If you get a Z-score that's less than negative 2, then these are significantly low values. If you get a Z-score that's negative 2 to positive 2, these values are non-significant. If you get a Z-score value that's greater than 2, these values are significantly high values. Example 1. In a sample of platelet counts, the mean was found to be 239.4 thousand cells per microliter, with a standard deviation of 69.2 thousand cells per microliter. The lowest platelet count in the sample group was 75,000 cells per microliter. Is this platelet count statistically significant? So I'll give you a minute to work on that. And type into the chat your answer. So is this platelet count statistically significant? Yes or no? So I'll show you the formula. You need to know the mean, the standard deviation, and is the Z value greater than negative or less than negative 2 or greater than positive 2? So I'll give you a minute to work on that and type into the chat what you found when you have your answer. Okay, so is this a statistically low enough sample count? So what I got when I did this is basically the Z-score is equal to X minus X bar over S. So X is equal to, the sample group was 75,000 cells per microliter, subtract the mean. So the mean was found to be 239.4 thousand cells per microliter, and then divide by the standard deviation, which is 64.2 thousand cells per microliter. So then all that you have to do, since all the units cancel, this is a unitless feature, the z-score, obviously. It has no units, yeah. So 75 minus 239.4 equals negative 164.4 over 64.2 divided by 64.2 equals negative 2.5. So statistically low. So the so the platelet count is statistically low, negative 2.5, because it's less than 0.2. It's less than 2, so that means that there's significantly low values or statistically low values. Okay, so percentiles. Percentiles measure the location of data point within the ranked data. For example, 50th percentile, P50, has about 50% of the data above and 50% of the data below this percentile. This means that 50%, that P50 is the same as the median. Percentile value of X equals the number of values less than X divided by the total number of values times 100. Always round to the nearest whole number. Example, the following list lists 40 cotinine measures in nanograms per mil in smokers. The data is already ranked in order. Find the percentile for cotinine of 198 nanograms per milliliter. So 198 is right here, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 in every row, 10 values in every row. So that's 20 values, 21, 22, 23. So there's 23 values. Actually, there's 22 values less than. So there's 22 values less than 198, right? So the percentile value is equal to the number of values less than X over the total number of values. So there's 10, 20, 30, 40 values in total. And then we multiply that by 100. So 22 over 40 will give us the percentile of 198. So 198 222 divide by 40 is equal to 55 percentile. Always round to the nearest whole number for percentile. So this is the 55th percentile for cotinine. And it's always nice to finish off with a sentence. All right. So let's see if we can make it through quartiles. Quartiles are specific percentiles that are used to determine certain measures of relative standing, such as interquartile range. The 5-number summary, which are used for box plots. The 5-number summary is the minimum value, Q1, first quartile, or P25, Q2, the second quartile, P50, Q3, the third quartile, P75, and maximum value. If a quartile works out to be in between two data values, take the mean of these two data values. The interquartile range is calculated by IQR, which is Q3 minus Q1. Again, if quartile works out to be in between two data values, take the mean of those two data values. The IQR represents the range between the central data points that are close to the median. Okay. Using the same cotinine data from example 1, calculate the 5-number summary and the IQR. So the minimum value is equal to 0. The 25th percentile is equal to 86, or Q1 is equal to P25 is equal to 86. Q2 is equal to P50, which is equal to 167. So I'm just numbering off the values. So there's number 10, number 20, number 30, and number 40. So Q3 would be equal to P75, and that would be equal to 250. And the maximum value would be equal to 491. So that's the 5-number summary, is that basically you just want to pick out the 25th percentile, which is the first quarter, the second quarter, the third quarter, and the fourth quarter is the maximum value. And then the minimum value is the absolute lowest. All right, so let's go through box plots. Box plots. A box plot is a graphical representation of the 5-number summary. It can be used to identify skewness, which shows up clearly on the diagram. Procedure for making a box plot diagram. Find the 5-number summary, draw a line segment from the minimum value to the maximum value. Draw a box extending from Q1 to Q3 and draw a line at the median. For example, using the 5-number summary of the cotinine data, the box plot would look like this. So I'm going to draw a box plot. Actually, they already drew one. So the minimum value, the Q1, the Q2, the Q3, and the maximum value. Interpreting box plots. Looking at the following box plot for pulse rates of men and women. What do these diagrams tell you about the skewness of each of the data sets? Now, the skewness, I'm going to interpret that actually. I don't know if I have enough time to actually interpret it right now, but what do these diagrams tell you about the skewness of the data? So it actually tells you where the center is if the center is closer to the left or if it's closer to the right. Now, if the center is closer to the right, remember that it's going to look more like the left foot, right? Remember, so it's going to look more like the left foot, and if the center is closer to the left, it's going to look more like the left toe. So this one would be left skewed. This one would be right skewed. All right. And then if I was to draw a box plot for this one, I would have my minimum value would be here 0. My maximum value would be here at 491. My Q1 value would be here at 86. My Q3 value would be here at 167, and my Q4 value. So this would be skewed to the left. Yeah. Anyway, that's it for today's class. But today's class, we covered a lot of ground, actually. We covered percentiles, we covered Z-scores, we covered standard deviations for frequency distribution tables. We looked at variance. We looked at calculating ranges. We also discussed about variation, what it means to have low variation as opposed to high variation. And I'd just like to thank you all for coming to class and paying attention and putting in the effort. I'm going to now stop the recording, and I will put up this recording on YouTube just for those who need it. Okay, so I'll stop.